For most of history, the horizon had an advantage over us. A ship in fog, an aircraft in cloud, or a storm over open water could already be moving, already be dangerous, and already be shaping events before anyone knew it was there. That was the old arrangement. Distance hid things, weather hid things, darkness hid things, and the element of surprise usually got the first move. Radar changed that arrangement. It taught humanity to do something that would have sounded absurd only a little earlier. It learned to see with echoes, not echoes of sound, but echoes of radio energy. A signal goes out, something answers back, and suddenly, emptiness is no longer empty. That is the heart of this story, and it matters more than the machines alone. It was buying time for a pilot, a ship, a controller, a forecaster, and for judgment to arrive before impact. That is the central tension in the history of radar. How did humans learn to sense what the eye could not yet see? And how did that strange ability become one of the quiet systems modern life now trusts every day? The answer was not brighter lights or sharper eyesight. It was a conversation with the dark. The science came before the machine. In the 19th century, James Clerk Maxwell described electromagnetic waves in theory, and Heinrich Hertz showed that they were real and could reflect from metallic objects. That mattered because reflection meant possibility. If radio waves could go out and return, then perhaps they could reveal something hidden between those two moments. In 1904, Christian Hülsmeyer demonstrated a device called the telemobiloscope. It could not do everything later radar would do, but it used reflected electromagnetic waves to detect ships in poor visibility, and that made it a remarkable glimpse of the future. The idea did not suddenly conquer the world, because history is rarely that considerate. Useful ideas often appear once as prophecy, then again later as infrastructure. In 1922, Guglielmo Marconi urged the use of radio waves for detection, and that same year, A. Hoyt Taylor and Leo Young noticed that a passing ship disturbed radio signals across the Potomac in a meaningful way. The clue was sitting right there in the interference. Then, in 1930, at the U.S. Naval Research Laboratory, Lawrence Hyland and Leo Young detected an aircraft during radio experiments, and A. Hoyt Taylor helped turn that discovery into a practical line of radar research. At that point, the essential truth was no longer theoretical. The sky itself had started answering back. A clue is not yet a tool, and a tool is not yet a system. A system matters only when people learn how to trust it. Britain felt that pressure early. Before radar fully matured, some early warning efforts relied on enormous acoustic mirrors, giant concrete listening devices meant to hear aircraft before they could be seen. They were ingenious, and they deserved their share of respect. They were also a reminder that ingenuity and adequacy are not the same thing. In 1935, Robert Watson Watt helped demonstrate a practical radio-based aircraft detection system, and Britain moved quickly from experiment toward deployment. This was not a leisurely research exercise. It was a race against distance. By the late 1930s, chain home stations were being built along the British coast, creating the first operational early warning radar network of its kind. They could detect aircraft at long range and give fighter command what it almost never had enough of: warning. But the deeper achievement was not the tower. It was the chain. Operators watched green traces on cathode ray tubes. Plotters translated those returns into positions. Controllers combined reports, judged what mattered, and directed fighters accordingly. That is why the story matters so much during the Battle of Britain. Chain home and chain home low did not replace pilots, nerve, or judgment. They made those things usable in time. Radar did not make people omniscient. It made them less blind. That turns out to be enough to change history. Then came the great acceleration. If the early years proved that radio detection was possible, the next phase made it vastly more powerful. In 1940, the British magnetron crossed the Atlantic with the Tizard mission, along with the knowledge to reproduce it. That exchange helped turn microwave radar from a breakthrough into a rapidly expanding capability, becoming one of the century's most consequential technological handoffs. At MIT in the United States, the Radiation Laboratory became one of the great engines of wartime radar development. Its work reached into shipboard search, airborne bombing, harbor defense, gun laying, blind landing, identification systems, and long-range navigation. This is the point where radar stops being a promising specialty and starts becoming an ecosystem. Not one machine, but a family of systems for different conditions, with operators learning how to read each one. An early radar equipment was not exactly graceful. A fair amount of it had the aesthetic charm of furniture that had enlisted. Still, elegance was not the assignment. Performance was. Microwave radar helped aircraft find submarines, helped defend convoys, helped guide aircraft in poor visibility, and helped counter the V-1 threat to London. The United States Navy also gave the technology the acronym RADAR in 1940, which was much kinder to ordinary conversation than saying radio detection and ranging every few minutes. This is where the radar story becomes unmistakably American in scale. Britain made a crucial leap, but the United States turned that leap into enormous industrial and research momentum. Radar had become not just a breakthrough, but a capacity. After the war, radar did not disappear with the uniforms. It kept working, but now much of its work became quieter. In aviation, radar transformed air traffic control. In 1946, the Civil Aeronautics Administration opened a radar-equipped airport tower for demonstration purposes, and by 1950, the first airport surveillance radar systems were beginning to enter service. That may sound procedural, but the consequence was deeply human. Crowded skies had become more manageable because controllers no longer had to rely only on estimates, radio calls, and hope. At Washington National, radar departure control began in January 1952, and later that year, radar approach control followed. A glowing blip on a scope is not dramatic cinema, but it is an excellent way to prevent metal from attempting a passionate union at high speed. Weather radar followed a similarly important path. After devastating mid-century storms and hurricane seasons, the U.S. Weather Bureau built a broader radar network, and in 1959, the first operational WSR-57 was commissioned in Miami. That alone improved warning, but Doppler radar changed the picture again. By measuring frequency shifts in returned signals, Doppler radar could reveal motion, not just presence. At the National Severe Storms Laboratory in Norman, Oklahoma, Doppler work helped demonstrate that this technology could materially improve severe weather warning. That research fed into the operational WSR-88D, better known as NEXRAD, which brought a far more capable weather radar network into broad use in the 1990s. Later, dual polarization upgrades improved radar's ability to distinguish among rain, hail, snow, and various kinds of clutter. Forecasters were no longer just seeing storms more clearly. They were understanding them more precisely. That is one of the loveliest turns in the whole story. A technology pushed forward by war became one of the reasons families now get better warning before a tornado, a squall line, or a landfalling storm. Radar's story did not end at airports or coastlines. It kept climbing. Synthetic aperture radar, or SAR, allowed aircraft and later satellites to create detailed images day or night and through cloud, because radar does not need sunlight and is far less bothered by weather than ordinary optical imaging. That opened an entirely different kind of sight. When NASA launched CSAT in 1978, spaceborne SAR proved it could watch oceans, sea ice, coasts, and land from orbit with a new level of consistency. Radar was no longer only warning us about what might arrive. It was helping us study the planet as a system. Radar altimeters in orbit extended that watch by measuring sea surface height and helping scientists track the shape and motion of the ocean with extraordinary precision. In that sense, radar became part of humanity's long effort to measure change before it becomes crisis. And then radar went farther still. Cassini used radar to peer through the thick haze of Titan, Saturn's largest moon, revealing lakes, channels, and surface features that visible light could not show nearly as well. That is such a beautifully strange destination for this story. A technology born from fog, ships, coastlines, and fear eventually helped reveal landscapes on another world. Radar began by asking what is out there in front of us. It eventually became a way of asking what is out there, period. So what is radar really when the whole history is taken together? It is not just a machine that finds objects. It is a system that turns delay into knowledge. A pulse leaves. A return arrives. Between those two events, distance becomes measurable, movement becomes interpretable, and uncertainty gives up a little ground. That is why radar has endured across so many settings. It helps controllers separate aircraft, helps meteorologists watch dangerous storms organize, helps ships navigate, helps scientists map ice and terrain, helps satellites read the ocean, and helps spacecraft study worlds hidden behind haze. The most important thing it ever produced was not an image, not a sweep, and not even a warning tone. It was time. Time to react, time to decide, time to protect, time to understand. And perhaps that is why radar feels so quietly profound. It did not make humanity all-seeing. It simply narrowed the space in which surprise could rule us. Radar changed history by shrinking uncertainty from the first reflected waves to coastal towers, from wartime laboratories to airport scopes, and from tornado warnings to Saturn's moon Titan. It taught us that darkness is not always silent, distance is not always empty, and the world often answers back when we learn how to ask. From unseen danger to invisible guidance, your echo is always welcome here at Illumentary.